It's like a half marathon.
Yeah, like there was a mountain that was like a mile and a half long. And it was like.
Oh, yeah.
Right.
Okay. Like the gang's all here. The faithful 1%. That's ones that clean up after a work party. How can I help? What questions do you might have?
Can you go over all of the right hand rules and what the fingers mean and how to use them?
Yes. The right hand rule. Print off. There's only one right hand rule that gives you a force. Okay, so if I divide this between force, an actual push, and field, this would be right hand rule number 1. Now, I understand that some of the PAs in the help center are doing some sort of Spider-Man right hand rule. No, don't do that. No Spider-Man. Okay. When you're doing the right hand rule, there has to be a velocity, and whether that's a single particle racing across the room or whether that's a whole bunch of charges flowing through a wire, we call that conventional current. That's the motion. Okay. And because there has to be motion, you reach that direction first. And then the important part of this whole right hand rule is to turn your wrist until you can wave in the direction of the B field. That turning of your wrist is going to force your right thumb in the direction of the force on a positive charge or conventional current. Okay. If it's an electron, switch it. So that's right hand rule. And so if I had a B field and a V velocity, first of all, you should know that you don't have to be that gifted with the right hand rule number 1. If I can draw velocity and magnetic field on the same piece of paper, the only possible directions for the force are out of the page or into the page. And so you just have to be good enough to know which it is. The force is always going to be perpendicular to these two vectors. Okay. And so in this case, I would, and here's just a suggestion. You're going to have much more positive experience with right hand rule number 1 if you turn your page so that you're reaching away from your body and keep your hand close to your page where you've drawn your vectors. You know, I see some people, you know, looking at their page and doing the thing up here and then trying to figure out what that thumb means. But if I take it right along my page and then turn my wrist so that I can wave in the direction of the B field, I won't get myself messed up. Now, when it comes to the magnetic field, if we have a long straight wire carrying current, use right hand rule number 2. You've got a straight part of your hand, you got a curved part of your hand. And you know that for a straight wire, the magnetic field is a circle around it. We just can't remember which way it goes around it. And that's why we use right hand rule number 2. It's just a memory device. And if my current goes in a loop, either a single loop or a solenoid, a lot of loops. Well, now you've got a curved part of your hand and a straight part of your hand. Let the curved part of your hand represent the current, and so we use right hand rule. Oops. Oops, I'm off the page. Number 3. Okay, now often we draw a current loop like half a donut. And if I have current going away from me there and towards me here, it would be going down the back. I'm looking at the back half of a donut. If I looked on the side, it would look like that. And it would be coming down the back. Okay. Now, if I curl my fingers in the direction of the current, my thumb tells me the direction of the magnetic field at the center of the loop. But I also know that a current loop acts like a bar magnet. So I can also use that right-hand rule number 3 to tell me which side of that loop is the North Pole, if I were to replace it with a bar magnet. And that's what you should do whenever you have a problem that involves a current loop. As soon as you can, use your right hand rule number 3 and turn it into a bar magnet and go back to the second grade. Say, what would my second grade self do with this problem? You know, if I had this bar magnet sitting on the table, what would I expect it to do if I were a second grader? I think more mistakes are made by trying to make loop problems harder than they are. Just trying to do fancy stuff when bar magnets will do it. I don't know, does that answer your question, concern? Good, sir.
Can we go over a bit on when it talks about a loop and it's not the current rotating, but like the loop itself rotating? Can we go over a bit of how we can tell which way it'll rotate when we're just given like the magnetic fields?
If you have a loop that can rotate, let's say I've got this not giving me the range of motion I need there. If I have a North Pole and let's say a current loop that is free to rotate about some center. Okay. Is that what you're asking about?
A little bit. I guess that more has to do with, I'll try to find a problem, but you can go over this if you want.
Okay. The first thing you do is you use your right hand rule to replace this with a bar magnet. And then you go one step further and say, well, if a bar magnet can rotate about its center, well, that's a compass needle. Okay, and I remember that a compass needle, the north side of that compass needle is the one that lines up with the Earth's magnetic field, or the magnetic field that it finds itself in. And so since magnetic field due to this bar magnet is away from the north, this thing is going to rotate counterclockwise until it lines up with that. Okay.
So in problems like these where we have a current like that, if we can find what the bar magnet is, we can find, like going back to the second grade, we can find out which way it'll turn.
gonna rotate.
rotate, yeah.
Yeah, and the other way to think of it is just, well, this north is gonna track that south, this north is gonna repel that north. Gonna rotate that way.
Let's say you have like north facing north and if the north is like slightly above the half, does that mean it's gonna rotate clockwise? If it's slightly below the half, it's gonna
I'm
rotate?
sorry, I'm very
Alright.
limited in my ability to hear.
So let's say the current loop was flipped around so that north was on the left side, right?
Okay,
And what's the indicator of like clockwise versus counterclockwise? If it's just slightly above half, does that mean it's gonna go
oh, yeah.
clockwise? If it's slightly below half, it'll go
So
counterclockwise?
which way is it gonna go if it's
If it's closer to,
really close? Um. So if I had the North Pole and I had this loop such that I had a north here and a south there. That's what you're asking.
yeah.
So again, look at the symmetry line. And if it's, we call this an unstable equilibrium. If it was perfectly lined up, it would be stable until you breathed on it. Okay? And that's like taking an upside down bowl and putting a marble right on the very center. You know, if you get it just right, it'll stay there until someone bumps the table and then it's gonna roll. And so if it's just a tiny bit above that center line, it's gonna go clockwise. If it's just a tiny bit below, it's gonna go counterclockwise.
So for the purposes of like an exam question, if it were perfectly in equilibrium, would we say that it's gonna stay there, or would we say that it's gonna go 180 degrees?
Well, you have to give me the benefit of the doubt that I would not put you in that situation. Okay, you know, in this sample exam question, it was like that. It was right. Yeah, this question here was one of those things where we had a south pole against a south pole, and it was just right lined up. And you'll notice my wording on part C, will the loop want to rotate? I didn't say, is it gonna rotate clockwise or gonna rotate counterclockwise? Because I don't know how it got bumped. But you know, it doesn't want to stay there with a south pole against a south pole. And so I could ask you, you know, is it happy there? Does it want to go somewhere else? But I wouldn't ask you to split hairs. Okay,
Could you go through this problem?
what is he saying?
Could you go through the problem?
With that?
You go through the problem. This.
Oh, go through the problem. Okay. Okay. So we are closing this switch. And so, and we're looking for the induced flux through this copper loop. And part A is asking us to go through the actual construction of the change in external flux. And so I know that the initial external flux is 0 because the switch is open. Now, if I close that switch, this is the positive terminal of the battery. And so conventional current's gonna go up the back and down the front, 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 and down that way. Now, if I use right hand rule number 3 and curl my fingers in the direction that the current is traveling, that's gonna lead my thumb to the right, and so there's gonna be the north side, that's gonna be the south side. Now, as soon as I close that switch, I suddenly have external flux that goes towards the South Pole. Okay, so my final external flux is gonna be to the right. What I care about is the change. What do I have to add to nothing to get something to the right? And that would be something to the right. Well, the and that's part A. Just find the change. So the direction of the induced current in the loop, well, I have to first of all say that the induced flux and by that I just mean the induced field lines have to fight the change. So if the change is to the right, the induced flux is to the left. And now I use right hand rule number 3 again. How do I get field lines to go to the left through that loop? Well, I'm going to have induced current going up the front and down the back. So up front, down the back. Now, that's going to turn this loop into a bar magnet with the South Pole on the right and the North Pole on the left. And since this loop can rotate about a center bar, that's what we were talking about with the unstable equilibrium. It's not going to want to be there, but I'm not really sure which way it's going to go. But chances are before the end of the minute, it's going to go.
Could we go over the compass problem? Go over this problem.
Oh, yes.
Thank you.
Okay.
Another sample exam question too.
Okay, so can you read that okay? Yeah, okay. Current carrying insulated wire is formed into a square loop in a vertical plane. A compass is held horizontally just above the loop. The wire loop is shown. And here we want the current in that loop to be big enough that the magnetic field due to the loop is so much stronger than the magnetic field due to the earth that we can neglect the magnetic field due to the earth. Okay. Now, the question is, if the current is going as shown here, what would the compass needle look like? Well, here we are testing a couple of things. We're testing your ability to wrap your head around three-dimensional problems because you've got to figure out what the magnetic field looks like on the side view, and then you got to look from the top. Okay, and here's where having props really makes a difference, okay? If, you know, Josh in one of the classes, went and bought a bunch of, um, pipe cleaners. I think he went online and brought them. And anyway, he's got more than he needs, so find him and hit him up for a couple. But, you know, you can make loops, you can use them to represent field lines, all sorts of fun things like that. So in this case, if you don't have something like that, just use your fingers and say, well, if the current's going around counterclockwise, as I'm looking at it from this side view, that means the north is out of the page, okay? And here's where the problem's a little tricky, because if I put that compass in the center of the loop, it would line up with out of the page. But I didn't. I put it on top of the loop. And remember, since the loop acts like a bar magnet, the field lines come out of the north and then wrap around to get back to the south. So the magnetic field due to this current is going to come out of the middle, and then it's going to go wrapping around outside of the loop to go into the south. Now, here's where you use your fingers again. Outside of the loop, it's going into the page. Whoa. If I, that too. Okay. Outside of the loop, it's into the page. If I just rotate my finger there, it's going to be going this way. So the compass needle would point like that. We okay? Okay. Well, now we bring a, we still have this current in the loop, but now we bring a north pole nearby. And I know that I've got this due to the loop, and I'm going to have this due to the bar magnet, and that's going to give me something in between. So if I draw that bigger, it would point something like that. Is the magnitude of the magnetic field at the compass in part B greater than, less than, or equal to the magnitude of the magnetic field of the compass at the compass in part A? Well, if we believe Pythagorean's theorem, the magnetic field that it's experiencing now has a portion that is due to the Earth and a portion that is due to the loop, and the total magnetic field is going to be the vector sum. And the hypotenuse is always the longest part of a triangle, and so it's going to be bigger. Okay, and you could say B total is going to be the square root of B Earth squared plus B loop squared as your justification, but you don't have to justify it because you're taking a multiple choice test. You can just say because it's Tuesday, and it's, I said because it's Tuesday because 80% of you wait until the last day to take that exam. I feel sorry for the testing center. Yes.
You justify it as more field lines are going through that area now because we bring in another magnet?
Oh, this is a magnetic force problem. We're not looking for induced current at all. We we're not saying as we bring up the North Pole, we're saying with the North Pole there.
Just like quantitatively, like we're adding more field lines in because we have another magnet present.
Oh, well, certainly the field lines for the total field would be closer together. But why that is because you're adding two vectors that are perpendicular to each
So that's the better.
other. Yeah, because if I had brought in that North Pole a different direction towards the east, I could actually make the total field smaller because they would be fighting each other, but because I made them perpendicular, it's got to be the hypotenuse. Now let's finish this. When this was given as an exam, this last part was a part that really caused people grief. And again, it's because of the three-dimensional nature of it. We said that with this current going around this way, that the North Pole would be out. And so if I again use props and say, here's the North Pole of the actual bar magnet, and here's the North Pole of the loop, and the loop's free to rotate. Well, this North Pole doesn't want to be next to that North Pole, and so it's gonna tip this way. Now, another way of doing that is to say, well, the magnetic field lines come out of the north and then spread apart. And so if I looked at if the current comes up this side, it's going to the left on this wire that's closest to the magnet. And so if I use right-hand rule number 1 to find the force on that top wire, I would turn my page so that I could reach in the direction of the current. I would turn my wrist so that I could wave in the direction of the B field, and my thumb would be the force on that wire would be out of the page. So it would tip, the top would tip out of the page. Either way you argue it, the thing rotates with the top out of the page. That answer your question?
Perfect, thank you.
Yes.
So it seems like, the circuit and stuff. Like the part that's always at the end of part 3, when you open the switch back up. When you have the way you approach it differs if there's resistors versus light bulbs.
Slightly different.
Like if it's voltage or current.
So if I have resistors, I can actually find what the current is, and I can use V equals IR to decide how big that voltage across the inductor is. I say, well, I need this much current to keep going through the inductor. It's got to go through these 3 resistors. V equals IR means I got to have a total of, 96 volts, and the capacitor is only giving me 12. So I can very quickly get a number. With bulbs, you've got to be a little tricky. Because we don't know how many amps are flowing, but we can predict how many volts are across the bulbs. We say, we still think about current, but with some waffle words. The current is big enough in this bulb B to make it 12 volts bright. And then if it's in series with these other 2 bulbs, they must have the same amount of current. I don't have a number for that, But I know that if it made bulb B 12 volts bright, it's gotta make these guys 12 volt bright. And there's 3 of them, so I'm gonna need 36 volts here. So it's just a one extra step in the reasoning. It's easier with the resistors.
Something
And in the back, oh man, if I have a heart attack, if I fall down and never get back up, my wife's gonna be so mad at you.
Something that happens is that those bulbs weren't on. Because the inductor is like 0.
Yes.
And so then it's like, how much voltage do these bulbs now have? Because it's like, we knew that like 6 volts was going across it to get to the bulb that used to be on over here, but now it's gonna be off or something like
Yes.
that. So that's like, why do those ones get 6 volts, why do they not get 2 volts?
I'm glad you brought that up, okay? This, of course, is from that homework. In part B, we had um, because this capacitor was full and was acting like an open switch, these guys are dark and they're 0 volts. And this one is in series with A now. And if it's a 12 volt battery like it was in your homework, this is gonna be 6 volts and this is gonna be 6 volts. And this is gonna be 0 volts, okay? Now, in part C, we suddenly throw the switch open and suddenly A is out. And when I open that switch, it's as if A and the battery don't even exist anymore. Okay? Now, the only thing that can't change is the charge on the capacitor and the current through the inductor. Those have to stay the same. A can change. It had 6 volts and then suddenly it had nothing. C can change. It had 0 volts and suddenly it has 6 volts. D can change. It had 0 volts and suddenly it had 6 volts. B can't change because it was in series with the inductor. And it's not that B couldn't change if it was put somewhere else, but because the inductor current can't change and B's getting exactly the same current, they're right in line, they're in series with each other. That one can't change. If it was 6 volts before, it's still 6 volts. But because I've got a single loop now and C and D are in series with B, if B still has enough current to make it 6 volts, suddenly they do as well. It just, pow, it's no time at all. Because the only thing I can't change is the current through the inductor and the charge on the capacitor. Does that answer your question? Oh, you're gonna say no, and then I've got to go all the way back up there.
So no, that one made sense to me when I did the homework.
What's that?
That one made sense to me when I did the homework, but this one. This is like its own little mini circuit.
Oh, yeah.
This is its own mini circuit, and none of these are on. Why is it that there was 6 volts passing
Oh,
across this to get to this one? So why is it not 6 volts in and 12 all the way over here? So it's 666, and then is that because of this 6 volts?
yeah, because the current that goes through the inductor in part B is the current that went through bulb A.
Exactly. yeah.
Okay, and E. And so, since this is 6 volts and that's 6 volts, that tells me how much current is going through here. It's enough current to make a single bulb 6 volts.
So that means these have to be 6 volts.
That has to be 6 volts.
Oh, and you're not gonna split that across all three.
Well, because the same current that goes through D is going through C and going through B,
This is just gonna magnify that.
yeah. It's gotta keep the same current. What that current has to go through, the inductor doesn't care. That inductor will do whatever it takes to, and we saw that in our problem, one of the earlier problems with resistors. We found that when the inductor stopped fighting and we only had 5 ohms in the circuit, we got up to 40 amps. It was a huge current through the inductor. And then suddenly we threw the switch open, and instead of that current going through a 5 ohm resistor, it had to go through a 45 ohm resistor. Well, suddenly that inductor turned into an 1800 volt battery, huge, just because it had a huge current going through it before. Still has to have that huge current. I could have made that other resistor over there 1,000 ohms, and then it would have turned into a 40,000 volt battery. You know, that's why inductors are dangerous, is because they can suddenly have a huge voltage across them to keep the current flowing. Greg?
Will capacitor and inductor ever cancel each other out?
No. No, and that's because first of all, in these problems, the conventional current's always leaving the positive terminal of the battery and coming down one of the paths. And so the current through the inductor is always going to try to be going down, and the charge on the capacitor is always going to be positive on top. And so they're always going to be pushing in the same direction. Yeah.
I'm sure we wouldn't be tested on this, but just out of curiosity, is there ever a scenario in which you have 2 inductors that have opposing currents?
Oh, it's too late to change the exam. That would have been so much fun. No. So you're saying, if I had, let me
So I have
think
an
of such
example.
a scenario. If I had a symmetric situation where I had 20 ohms here and 20 ohms there. And I had, say, 60 volts. Okay, that's an inductor here, and that's an inductor here. And so during our part B, a long time after the switch is closed, the 2 inductors turn into wires. And so I would have 3 amps going down here and 3 amps going down here. When I open the switch, these things are going to want 3 amps to keep going through them. And so this is one of those dangerous situations where the only path left to them would be across that switch. And so they would both turn into huge batteries to jump that switch and throw a spark. Yeah. Clever. No, I'd never do that on an exam.
Can you go over number 3 on the first sample exam?
Sure. Are we talking about that problem there?
Yes.
Okay. So we have a situation. You want to look for the word induced in problems. When you see that, that means you're going to be doing this construction where we have the initial external flux, the final external flux, the change in flux, what is the induced flux, what kind of induced current causes that. We've been through that little step-by-step reasoning several times here. So here I would say the external flux initially, and again, if I'm looking for the induced current in the loop, external means everything that's not the loop. So in this case, it would be the bar magnet. And I know that for a bar magnet, magnetic field goes towards the south. And so I'm going to have a magnetic flux down. Now, when that bar magnet gets further away, the field is still going to be towards the south, but not as many field lines are going to make it through the loop. And so my external flux gets smaller. And then the question is, what do I have to add to this long vector down to get a short vector down? I have to add a vector up. So my change in flux would be up. Now that means that my induced flux has to be down. And so at this point, I use my right thumb to represent the induced flux, and my fingers curl in the direction away from me here and towards me here. Now, again, this requires you to think in 3 dimensions. If the current is going away from me on the left, when I pick that up and look from the top, it's going clockwise. Okay. So again, if you have props, you know, and if you forgot to bring props, take off your wedding ring, you know, and use that as your fun story. I used to be heavier, and I was visiting my son and daughter-in-law in Missouri, and my finger was just swelling. My finger was too big for the wedding ring that my dear wife had purchased for me when I got married many years ago, 47 years ago. And so we tried to get that wedding ring off. We tried every trick in the book. And finally, we went down to the fire station, and a bunch of burly firemen that should have been on a calendar. They laughed and laughed and laughed as they tried to yank that. They were trying to yank my finger off, and finally they ended up bringing out the jaws of life and cutting that thing off of me. So anyway, I got a $5 replacement that fell off of my finger while snorkeling in the Galapagos over Christmas break because I had lost 90 pounds. And so just like Gollum, the one ring left me at the worst possible time. So, okay, that's not going to be on the exam. What is going to be on the exam? Yes.
Could you explain if it's, yeah, could you explain motors and generators again?
Uh-huh. Yeah, motor and a generator are essentially the same thing. Just a coil in an external magnetic field. And if that coil is free to rotate about its axis, well, a coil acts like a bar magnet. A bar magnet that's free to rotate acts like a compass needle. And that's always going to want to line up with the field it's finding itself in. So if there's a field that's set up, and usually you've got something like a horseshoe magnet in there, if you've got a field that's pointing towards the open door, and I have a dipole that's acting like a compass needle, it's going to want to line up, okay? And it'll line up and stop. And that's not a good motor, okay? But if when it lines up, you can flip the current so it still needs to line up, and then you flip the current again so it still needs to line up, and you keep doing that, then it keeps turning. But you have to flip the direction of the current every half turn so that it's always trying to line up. Now, that's a motor, and we flip the current with engineering. We make sure that the leads are touching just the right place at just the right time to get the current in just the right direction so that it has to line up. Takes a lot of thought, okay? Once that loop is turning in the magnetic field, I'm changing the field lines through the loop, okay? And whenever I do that, nature sets up this induced current. Well, that induced current, you got to pay for, okay? Nature demands that energy be conserved. And so the direction of this induced current is always going to be the opposite direction that would be helpful. In other words, if current that would be helpful would be making the dipole like this so it wants to line up, the current that nature gives you is something like this that you got to force the other way, that you've got to fight to make it go the other way. And so the battery current is helping the motion, causing the motion indeed. And the induced current is fighting the motion. We call that the back EMF. Now, if you don't have a battery, if it's just a generator, you're out in the middle of the sticks and you just want to light up your RV, okay? You can turn that loop in the magnetic field a number of different ways. Gilligan did it with a bicycle. In class, we did it with a crank. You can use a gas motor to turn the coil. At a hydroelectric dam, we use falling water hitting turbines to turn that coil. However you do it, the more current you get through the coil, the harder it is to turn. And we saw that in our demo. We had someone come up and turn that crank. And as I turned on more and more lights, it got harder and harder and harder to turn. That answer your question?
We go over sample exam 2, question 3. I got the right arrows this time, but
Oh, okay. Okay, doke. There's my pen. This is another situation where we are closing the switch and we want to know whether this thing is going to rotate about its axis clockwise or counterclockwise. So we have to figure out the direction of the induced current in the copper loop. Well, we know with the switch open, the external flux, which is due to the solenoid, would be 0. When I close the switch, the bump here is the positive terminal of the battery, and the flat side is the negative terminal of the battery. So that means conventional current's going to go up the back and down the front. And if it goes down the front, by right-hand rule number 3, this will be the north side of that solenoid, and this will be the south side. Now, when that turns into a bar magnet, it sends field lines through the loop to the right, away from the north. And so the external flux, again due to the solenoid, after I close the switch, is to the right. Now the change in external flux is what I have to add to 0 to get something to the right. So that's going to be that way. And that means that my induced flux is going to be to the left, it's fighting that. Okay. And so in order to get field lines going through this thing to the left, the current has to go up the front and down the back by right-hand rule number 3. Now, that means that I've got a north pole. I can turn this loop into a bar magnet where this is the north pole and this is the south pole. And so once I turn that into a bar magnet, I go back to the second grade and say, well, what if I had one bar magnet glued down to the table? And I had another bar magnet that could rotate about that point there. Well, that north and that north don't want to be next to each other, so that's going to swing around like that. And so it would go counterclockwise.
That question right below it, number 4. How do we know what angle to use? Can you go over that again? Like for theta?
I didn't catch the last part. How do we know?
How do we know what angle to use for theta when we're
Oh.
setting this up?
The angle for theta is always going to be the angle between the velocity and the angle of the B field. This is always the theta that we use. And so I know that if this is 70 degrees, so that's 70 degrees. And I know that this, it has to add up to 90, so this is 53 degrees, right? So if I add 53 and 70, my theta is going to be 123 degrees. Okay. But again, it's useful to have props because sometimes one of them is out of the page. And this problem, they're both on the same sheet of paper, and so I can just draw it. But if the B field is north and down 70 degrees and the motion, the velocity is east, then it's useful to have those two, because you can't get up in this in the testing center and do this, they throw you out. But if you had two little pins that were like that, you could see that the angle's 90 degrees. And then it might be helpful to just practice before you go to take the test, you know. Well, what if it's going towards the ceiling? You know, what would that angle be? What if it's going south? What if it's going towards the floor? What if it's going east? What if it's going west? You know, do those sorts of exercises before you get in the heat of battle at the testing center.
If I use the other angle on the left side of the velocity arrow, would that still give me the same answer?
Yes, it will. Yeah, it turns out that you're taking the sine of that angle in the Lorentz force equation, and the sine of any angle is equal to the sine of 360 minus that angle.
Can you do an example where, can you do an example where the v field and the velocity aren't on the same plane, but they're not at 90 degrees?
Oh, so if they're not on the same page and they're not 90 degrees, I mean, if the B field was north and down 70 degrees and the velocity was east but up 37 degrees, we'd have to find this angle. And you could give me the rest of the night and into the morning, and I wouldn't be able to find that at my age. And so I would never, ever do that. No, that's, I don't know. I used to be able to do that, I think. I don't remember. I've forgotten so much.
Example exam 1B.
This one here?
Yes.
Oh, I can do it, but when I do it, you're gonna hate me. You're gonna say, oh, Greg, that was uncalled for. That was uncalled for. That was tricky. Okay. You've got a wire carrying current and it's placed on top of a magnet. And that wording is the key. It's on top of the magnet. It's not inside the magnet. It's on top of the magnet. And we know that magnetic field lines come out of a north but then they wrap around and go back into the south. So I'm going to draw two of those field lines, but they're in all directions, okay? So if I look right here, the magnetic field is going like that. Now inside the bar, the field lines go from south to north, but the wire's not inside the bar, it's outside the bar. Now, this is one of those problems, and there's many of them, where there's only two possible answers. If the current's either going up the wire or going down the wire. So you just try them both. If the current's going up the wire in a magnetic field that's to the right, the force is going to be down. If it's laying on top of the bar, then into the page is going to be down towards the floor. And so that's going to be um, the current is gonna be going that way. I guessed right. Just a lucky guy. Now, when we had problems like this, and we wanted to know, which direction it was going to give me a force like that, just think of all the possible options and then try them all, well, if it was going this way, and the B field, I know that the B field due to this, this current is going to be up out of the page. So if I try this velocity, well, the force would be this way for a proton. It's an electron. Again, I guess right the first time. I'm just a lucky guy. But if you didn't guess that one, you got 4 different right-hand maneuvers before you get to the right one. Just trial and error.
What about for D, could the force not, like, if the current was going down, wouldn't the force be going up? And how do you know if the force is up or down?
Oh, what is the direction of the current if the force on the wire is into the page? Yeah, so it's given in the problem. Oh, we run out of our hour. The test opens tomorrow, but I suspect that many of you will not be taking it tomorrow. So I'm teaching 3 classes tomorrow and kind of running from place to place, but Friday I'll be on campus and Monday I'll be on campus. So if you have questions, stop on by. Okay. Let's go and get some rest. Let me thank you about this.
Yeah, your name? Tyler? Meet you, Tyler.
Bye.
How we've been